Have you ever noticed how, on busy days in the city, people naturally form into lanes on the sidewalk? The same thing happens on escalators. When it gets busy, one side becomes the side for people who want to stand, and the other is for people who want to walk up the stairs. That behavior isn't planned, it just emerges. It turns out you don't always need a leader giving out directions to have an organized system, and that concept is key to understanding one of the newest revolutions in robotics. If you're keeping up with robotics news lately, you've probably noticed how much progress has been made over the past few years. Companies like Boston Dynamics and Unitrees are basically putting out a new video every other day showing off some major advancement they figured out. But modern robotics isn't just about single impressive machines. Amazon, for example, uses thousands of robots across their factories to automate many of the simple, repetitive tasks. Early on, these systems relied on computers that would plan out their routes and assign tasks individually. But as you can imagine, this became a lot harder to manage as the scale of robots increased. You can directly control a robot when there's just one or two of them, but when you have a whole factory filled with them, it just doesn't really work. So an alternative to manual control was needed. If you want to understand where a lot of the modern developments of robotics are going, you have to look past individual machines and start looking at how intelligence forms when they start working together. This behavior is known as emergence. Emergence is what happens when you take a bunch of simple agents and give them simple rules, and as a result, complex behavior appears. No individual agent understands or commands the whole group, but they can still produce very complex results. This happens all the time in the natural world. Think about colonies of ants. Individual ants aren't very capable or impressive, but together, colonies can do a lot of things that look surprisingly sophisticated, like forming bridges out of their own bodies to cross gaps. Obviously, they don't have an ant commander telling each ant where to stand or hold. Instead, each ant is following a couple of very simple rules. They move towards the goal, and if they feel weight from other ants on them, they hold the position. When enough ants follow those same rules, a stable bridge forms. No single ant has to understand or plan the structure, it just emerges from their interactions. So if biology can create complexity with simple agents, the question is, can we do the same artificially? Craig Reynolds, an expert on artificial life, had the same question. He wanted to figure out how complex natural phenomena like flocks of birds or schools of fish naturally appeared. In these groups, they're balancing two opposing goals: to stay close to the flock and also to not fly into each other. But how do they actually stay together as a group? And where do those smooth, fluid movements that we've all seen come from? In his paper, Flocks, Herds, and Schools, Reynolds showed how this behavior can appear and be simulated with a few shared rules that each individual in the group follows. Reynolds took these rules and used them to create a simulation called Boids. Every point you're seeing on the screen right now is one of these Boids. To create a realistic flock, every Boid should try to maintain some distance from its neighbors so that they don't crash into each other. They should also try to fly in the same direction. And they should try to fly towards the center of the flock to stay in one safe group. With those three rules, separation, alignment, and cohesion, no single Boid needs to know where the flock is going or what shape it has. It just needs to react to the neighbors around it. An important note is that as the flock of Boids grows larger, the problem doesn't become harder for each individual Boid. Complexity doesn't increase as the group grows because each individual member is only keeping track of its neighbors. So complexity is distributed across the entire group rather than being concentrated in a single central leader or computer. Even though each simulated Boid is basically just a particle on a map, the same lifelike flocking behavior is evident. The agents themselves aren't intelligent or impressive, but the rules are. And this model turned out to be very useful for other simulations in video games. From alien ecosystems that you see in the world of Zen in Half-Life, to underwater worlds like in Subnautica. And once you can simulate this kind of behavior, the next question becomes obvious. Can you do it with real robots? One of the earliest attempts to answer that question came from Harvard with a project called Kilobots. Kilobots were simple, cheap robots with very limited capabilities. Basically, they could just move around and communicate to each other with infrared light. But the goal wasn't to build impressive robots, it was to see what would happen when you put a bunch of simple robots together, all following the same rules. Instead of being controlled individually, Kilobots function through local interaction. A few robots, called seed robots, would act as reference points and would broadcast a signal. Each kilobot would measure how far it was from that signal, and then adjust its position based on its neighbors. Over time, those local adjustments created complex shapes across a flat 2D plane. And if part of the swarm failed or was removed, the system could adapt and repair the shape without any assistance. These kilobots were a valuable proof of concept. They showed that man-made emergence wasn't just something that worked on a computer screen or in code. It could also appear in the real world if you had the right hardware. But kilobots had very clear limits. They were confined to flat surfaces, short ranges, and controlled environments. To really push the idea further, swarms needed to move beyond the lab and into the third dimension. When most people think of drone swarms, the first thing that comes to mind are the choreographed light shows where hundreds or thousands of drones fly in formation to create very impressive shapes or structures. And those are impressive, but they're all centrally planned. They're controlled from a powerful central computer. Each drone is told exactly where to go and when to be there, and as a result, they don't have any autonomy. Research-focused drone swarms take a different approach. For example, researchers at ETH Zurich have demonstrated drone swarms where each drone operates autonomously. No single drone understands the whole formation. Each one is only reacting to nearby drones and to local information to maintain spacing and to avoid hitting each other. But when enough of them interact at the same time, coordinated behavior emerges. Autonomous vehicles, for example, don't need a central system to plan traffic for an entire city. Each car can adjust speed, spacing, and lane position based only on the behavior of nearby vehicles. The same idea also applies to environmental monitoring and search and rescue. Swarms of autonomous drones can spread out to collect information while avoiding redundant work, and as a result, the process will become much more efficient. In all of these cases, the real intelligence isn't stored in any one robot. It comes from having many agents following the same rules. So what does all of this really tell us? Simulations, algorithms, self-healing swarms, what's the point? There are a few key takeaways from all of this. First, emergent intelligence shows up when scale makes individual control impossible. When you only have a few independent agents, it's easy to control them directly. But once you start dealing with large groups that need to function autonomously, centralized control doesn't scale. It's like trying to micromanage an entire factory. At that point, you don't guide behavior by issuing commands, you guide it by shaping how your agents interact. Second, sometimes shared rules matter more than smart agents. Emergence doesn't require individual intelligence. It just requires many agents, shared rules, and local interaction. A single ant isn't very capable, but the entire ant colony is. The behavior from a flock of birds is more impressive than simply watching 1,000 birds fly in the same direction. And third, not all future robot swarms will look how you expect. A swarm doesn't have to be a cloud of drones, even though that's probably what we're all most familiar with. It can be a fleet of autonomous vehicles, warehouse robots, or any system made up of many autonomous units. Really, if there's one main thing for you to remember from this video, it's that you don't always need smarter robots to get intelligent behavior. You just need enough robots following the same rules. It's the same reason lanes form on busy sidewalks. Thank you very much for watching. Please like the video if you liked it, and dislike it if you didn't. And if you want to see more videos like this about robotics, emergent intelligence, and other topics I think are interesting, please subscribe.